Hello, AP Bio. This is our first video lecture. This one's going to be for Chapter 2. I've probably already said this in class, but just to remind you, if you're following along with the lecture outline, I'm going to go through these slides pretty quickly because I know that you can access this at any time to pause it as necessary. And Chapter 2 is a long one. There's a lot of stuff in Chapter 2. This might be the longest chapter in the book. So let's get started. So Chapter 2 is called The Chemical Context of Life. So here I have a picture. And I just realized I think I'm wearing the same shirt in this picture as I'm wearing in this video. Isn't that special? So this is the fam. This is my wife, my son Jack, my daughter Marie. In the background of this picture, there's the ocean. There's maybe a couple of hints of clouds. There's atmosphere. There's grass. There's sand. So in this picture, there are things that are organic that are made of are living, like the grass or the people. And there's things that are inorganic, like the sand, or the water or the atmosphere, but all the things in this picture are made of atoms and elements. They're all made of the same thing. So the reason in biology why we start with what seems like what actually is chemistry is because the building blocks of matter are also the building blocks of life. This slide, so this isn't that important of a slide, but the idea of reductionism, so reductionism is sort of a philosophy in science where if you want to understand something, you don't start with like the whole thing. You break it down to the small parts and start by studying something at the smallest level, which in the case of biology might be a cell or the organelles or the actual atoms that make up the organelles. You don't start with the bird, you start with the atoms that make up the bird, and then you get increasing complexity as you go on. And the reason why we're beginning with atoms is because we're going to reduce life down to the atomic level. Okay, so a couple definitions. You did this in like elementary school. Matter is anything that has mass and takes up space, so it has to have volume. So air is matter because it will fill a balloon. It has volume. It takes up space. An element, so the periodic table is the table of the elements, right? There's, I believe, 96 elements that occur naturally. So elements are substances that can't be broken down by chemical reactions. Obviously, you can split atoms, but that's an atomic reaction. So the elements are basically how we classify matter. A compound is two or more elements in some way covalently or ionically bonded together in some kind of reaction. Compounds are what are called emergent properties. So an example here is sodium chloride. So sodium chloride here on the right, that's table salt. Sodium chloride is a salt at room temperature. It's a solid at room temperature. You know what it tastes like. It's I mean, obviously you can have too much of it, but it's harmless if you eat table salt, right? Well, sodium is a solid at room temperature, and sodium, elemental sodium, will explode. You've probably never seen this before because sodium will react with the moisture in the atmosphere, just in the classroom, where it will start to fizz. If you threw this block of sodium in a body of water, it would explode. Chlorine by itself is a gas. We're talking about like World War I, World War II, chemical warfare. So obviously sodium and chlorine elementally are very, very dangerous. You put them together, it's a solid, and it's pretty harmless. So the emergent properties of sodium chloride are things that emerge because you put sodium and chloride and chlorine together. All right, so the compound of sodium chloride, the elements are sodium and chlorine. I said before, it is 96% of all life is made of only 4. Actually, I didn't say this. I said that there were 96 naturally occurring elements, which I still think is true. About 96% of organic matter is made of only 4 different elements, and this you need to memorize. It's carbon, oxygen, hydrogen, and nitrogen. So about 96% of you are just those 4 elements. Those are sort of the elements of life. The remaining 4% are made of trace elements like phosphorus, sulfur, calcium, potassium. These are things that your bones might need, like, or how about in your blood? Your blood has hemoglobin that carries oxygen, gives it the red color, and hemoglobin has a trace of iron in it, so you need a little bit of iron in your diet. Iodine is an element that you need for your thyroid gland in your neck. You don't need very much of it though, so they're called trace elements. So atoms, like we say, the smallest unit of something that still has the properties of that something is called an atom. So the smallest thing of gold is called an atom of gold. You can break atoms down into subatomic particles, but then it's no longer gold. In the three main particles, you've learned this before, neutrons, protons, and electrons. Neutrons have no charge, they're neutral. Protons have a positive charge, and electrons have a negative charge. Neutrons and protons are about the same size. Electrons are much smaller. They're about, I think it's 1/2000th the size of a neutron or a proton. So if you were an electron, looking back at the nucleus, looking back at a neutron or a proton, it would be 2,000 times bigger than you are, which is why the electrons don't contribute much to the mass of the element. We'll get to that in just a minute. Actually, we'll get to it right now. So the unit Daltons, you don't really need to know that, but the unit Daltons is a unit of mass that we use for atoms. And electrons are about 1/2000th the size of a proton or an electron. So let's say that I ask you to draw an atom of helium. So helium looks like this, all right? Where the numbers come from, we'll discuss in a minute. Helium in the nucleus has 2 protons and it has 2 neutrons, all right? So there's 4 things in the nucleus. If I asked you what the charge was on the nucleus, you would say +2, all right? Because the neutrons don't have a charge, right? And then it has 2 electrons, which orbit around the nucleus in what are called orbitals. This is very, very oversimplified. When you took chemistry, I'm sure you did s orbitals and p orbitals and all that kind of stuff. Fortunately for bio, we don't really need to get into that, which is good because I don't enjoy teaching that. If I asked you the overall charge of this atom, you would say 0 because +2 and -2 sums to 0, okay? What would the charge be of helium if I took an electron away? If I took one away, the overall charge on the atom would be +1. If you remove a negative charge, you're left with a positive charge, right? What if I gave helium an additional electron? If it had 3 electrons, the overall charge would be -1. Because if you had 3 electrons, you'd have -3 and then +2. So overall, it would be -1. So helium is a neutral atom. And if you inhale helium from a helium balloon, it doesn't electrocute your lungs. So helium is very inert. It's a neutral atom because the number of protons and the number of electrons is the same. Okay? All right, cool. So again, this is chemistry, right? But we need to do this to get into organic molecules. So we define what the atom is by the number of protons. All right, the atomic number on the periodic table, which we're going to get to this bad boy in a minute. The atomic number is the number of protons. So if something has 6 protons, for example, 6 protons is carbon. So if something has 6 protons, it is carbon, no questions asked. The number of neutrons, the number of electrons could actually change. But if it has 6 protons, it is carbon. That's called the atomic number. All right. The mass number is the sum of the protons and neutrons added together. So the mass number is the mass of the nucleus, which is where the protons and the neutrons are. If you look at the mass numbers on the periodic table, so like look at carbon, the atomic number is 6. The mass number is 12.01. If you look at the atomic numbers, they're always integers, right? You can't have decimals because you can't have half a proton. The atomic weights, you can't have decimals because those are averages. And we'll get to why you have averages in a minute, okay? So the atomic mass of carbon is 12.01. We're gonna sort of round that to 12. The atomic number is 6, okay? So atomic number, number of protons, mass number of protons plus neutrons. This is a typical nomenclature that we use to write elements. So sodium, this little fraction, 23/11, the top number, the superscript, I guess you could call it, is the mass number. And the bottom number, the subscript, is the atomic number. So if I gave you this notation, you should know what this means. You should know that sodium has a mass number of 23, an atomic number of 11, and you should know what that means. So if I asked you for protons, electrons, and neutrons, the PEN for sodium, well, the atomic number is 11, so it has 11 protons, right? That's for sure. If the mass number is 23, how many neutrons does it have to have? Well, that has to be 12 because those have to add up to 23. So protons is 11, neutrons is 12 to add to 23. Now the electrons, if we assume this is elemental sodium, which we do because there's no charge, it doesn't say Na+1, it just says Na, then the electrons has to equal the protons. So in review, sodium, as drawn here, has 11 protons, 12 neutrons, and 11 electrons, okay? Any element that I gave you, if I gave you this information, you should be able to do that. This symbol for helium would be a helium, an He, with a 4 on top and a 2 on the bottom, because helium's mass number is 4. We're rounding. Actually, if you look at the periodic table, it's actually, no, there are no isotopes of helium, so it's actually 4. So for helium, it would be 4 and then a 2. So mass number of 4, atomic number of 2. For carbon, let's round. So carbon, if I asked you what it was for carbon, it would be a 12 over a 6 and then a C. So carbon, and again, we're rounding here, has mass number of 12, atomic number of 6. So that means it has 6 protons, 6 neutrons, and 6 electrons because it's not charged, okay? What if I gave you this and said it was sodium with a plus right here? Either a +1 or just a plus sign. So sodium is usually positively charged, right? So if this was Na+, that means it has 1 more proton than electron, right? Well, you can't change the number of protons. So in the case of Na+, it would have 11 protons, 12 neutrons, but only 10 electrons if it was positively charged. So if I gave you this, or any of the notations like this, you should be able to tell me the PEN, the pen, the protons, the electrons, and the neutrons. Okay, isotopes. So why are these averages? So the atomic number, the number of protons, cannot differ for an atom. If it does differ, it's a different atom. If I give you gold and you change the number of protons, it's a different atom. It's not gold anymore. But the number of neutrons can vary, and those are called isotopes. You know, iso means equal. They have equal numbers of protons, but different numbers of neutrons. Ones that are radioactive means they decay. And this isn't physics class. We're not going to discuss how or why they decay, but the number of neutrons in the nucleus can change. The best example, well, so some applications, dating fossils, we'll get to in a minute, that's carbon dating, tracing atoms through metabolic processes, or diagnosing medical disorders. So this is some kind of scan of an individual where you've injected them with radioactive iodine. This is your thyroid gland in your neck, and your thyroid gland needs iodine. If there's too much iodine, it could be thyroid cancer. And they've made the iodine hot. They've made it radioactive. It's not really hot, although actually it could be giving off heat. But in whatever scan this is, the iodine is glowing. And you can see if I inject iodine in your body where it's going by tracing the radioactivity. If you used a Geiger counter, the little handheld thing, it would like click on your neck, and it would not be clicking or making that sound around your toes, right? Because the iodine is going to your thyroid gland. So the best example is carbon. Carbon has it has 3 isotopes: carbon 12, 13, and 14. If you look at the numbers here, carbon 12 is by far the most common. If it's 12, that means there's 6 protons and 6 neutrons. Carbon 13 and 14 are both very, very rare. Carbon 13, again, the proton number has to be the same. 13 would mean it has 7 neutrons and 8 electrons. They're all carbon because they have 6 protons. Carbon 14 will decay into carbon 12 and carbon 13. And this is going to be covered in a later chapter, but that's how we can date when fossils died, how old a fossil is. Because carbon 14, if you think about it, if carbon 14 decays into 12 and 13, why is there any carbon 14 left? Why hasn't it all decayed? Carbon 14 is formed in the upper atmosphere due to ultraviolet radiation. So as long as there's a sun and there's an atmosphere, there's some C14 in the atmosphere, and you breathe in carbon dioxide, right? So as long as you're breathing in CO2, you have some C14 in your body. But once you die, you stop breathing, and the C14 decays down to C12. So based upon comparing the amount of C14 in the fossil compared to the atmosphere, you can tell how long ago something died. We'll cover that again in a later chapter. Okay, so switching gears, energy. So the energy of an atom, in terms of how an atom reacts, largely comes from its electrons, all right? Nuclear reactions involve the nucleus, which obviously can be very energetic, as in bombs or power plants. But for biology, we're not really concerned with splitting in the atom, but we are concerned with what the electrons are doing. So potential energy is the energy something has based upon its location. If you're standing or you're sitting on a roller coaster at the very, very top, if you're not moving, you have no kinetic energy, right? But you have lots of potential energy because of your location. A general rule of thumb that you should sort of memorize is electrons. The further an electron is away from an atom, the more potential energy that it has. And if you think about it, the nucleus is positively charged. The electrons are negatively charged, so they want to attract one another, right? So getting the electron further away, you had to push it away, right? These electron shells, the first shell, the second shell, the third shell, the further away they are, the more potential energy they have. The analogy of a ball going down a flight of stairs, the higher the stair, the more potential it has. And this is getting into quantum stuff that we don't really care about for bio. But like you can't be between stairs. You're either on the third stair or you're on the second stair. So an electron going to a higher shell took energy. An electron going back down to the first shell loses energy. So to get this electron up here, I have to either heat it or do whatever to it. When that atom gives off energy, it could glow, it could give off light. That's an electron going back down to a lower shell. So this is increasing energy, this is decreasing energy of the electron. When you took chemistry, you learned electron orbitals and electron shells. For bio, you need to know that, again, the further out, the more energy the electron has. The first shell can hold 2 electrons, max. If it only has 1, it only has 1. If it has 2, there's 2 in that first shell. The second and third shells can hold 8. And there are more shells beyond that, which we're not going to worry about. For biology, we're good with just this sort of simplistic description. So if an atom has 5 electrons, and I said, where are they? Well, the first 2 are in the first shell. There's 3 left. That second shell can hold 8, but you only have 3. So it has 3. If atom has 10 electrons, and I ask you, where are they? Well, the first 2 are in the first shell. There's 8 left. The second shell can hold 8. So it's a second shell that's full. That's a happy element. What if it has 11 electrons? Well, 2 in the first, 8 in the second. That gives you 10. There's 1 left. So the third electron shell only has 1 electron in it. That's actually sodium. That's not a happy element. It wants to lose that electron as soon as you possibly can. An atom's greatest desire, if atoms even have desires, is to have an outer shell. It's called a valence shell, is the outer shell, that is full. So 2 is a happy number, 10 is a happy number, 18 is a happy number, because those are your noble gases, right, that are very inert, because their outer shell is full. If it's not full, it wants to react. This is showing the periodic table, sort of, just showing the electron orbitals. So hydrogen has 1 electron. Hydrogen, really, if it's neutral, has 1 proton and 1 electron, and that's it. There's no neutrons, because overall there's no charge, and its atomic mass is 1, which means there's only 1 proton. If you looked at something like nitrogen has 7 protons. It's neutral, so there's 7 electrons. Where are they? 2 in the first and 5 in the second. And electrons, like if you look at carbon has 2 in the first and 4 in the second. Electrons like to pair up if there's more than 4. So like when there's 5, 2 of them get paired up. Like look at boron. Boron has 2 in the first and they're in a pair. And there's 3 in the second. You don't pair them up until you have more than 4. So like neon, it has 10, 2 in the first, 8 in the second, and it's basically 4 pairs of 2. If the AP exam gave you a diagram like this and asked you questions about it, you should understand it pretty well. If I told you the number of electrons, you should know where they go. So if I said that sodium has 11 electrons, there's 2 in the first, that's 2. There's 8 in the second, that's 10. And there's 1 in the third, which gives you 11. Okay? Beyond argon, we really don't concern ourselves much in AP Bio. Again, what an element does is based upon the number of electrons in the valence shell. So chemical reactivity, and again, slides that I'm going through pretty fast are things that I've either already said or things that you can go back and look at later. We're not skipping anything. We're I don't want to repeat things that I've already said. So a covalent bond. So let's look at hydrogen. Hydrogen has 1 electron. It wants to have 2, but only has 1. This is showing what's called an electron cloud, because electrons are actually more like clouds than point negative charges. We don't need to get into that. So molecular hydrogen is H2 gas. Well, the 2 electron clouds start to overlap, so it's as if each nucleus has 2 electrons. They don't, they're each sharing 2, but it makes their valence shell full, so the electron or the molecule is stable. H2 gas, so you've done this in chemistry. The notation you use, this little bar is a single bond. A single bond represents a pair of shared electrons. So H2 gas is a single bond between 2 hydrogens. Hydrogen can only form 1 bond. It has 1 valence electron. It wants to have 2. So it will form 1 bond, and that's it. You don't get H3 because that's not stable. A double bond, so oxygen, let's go back a second. Oxygen has 2 electrons in the first shell. There's 8 total. It has 6 in the second. It wants to have 8. So oxygen loves to form 2 bonds. Molecular oxygen, O2 gas, is a double bond between 2 oxygens. Each line represents a pair of shared electrons. So a double bond represents 4 electrons. Remember, each oxygen wants to have 2 additional ones. So it's sharing its valence cloud with another one. So it's like it has 8. Oxygen always forms 2 bonds, right? There's 6 valence electrons. It wants to have 8. So it forms 2 bonds. Not really always. If it's not 2 bonds, like ozone is O3, but that's very unstable. So a stable oxygen always forms 2 bonds. To get it to form more than 2, you have to like heat it really hot or put it under intense pressure or zap it or do something crazy to it. 4 compounds that you should really sort of have memorized. So H2, here we show the electron diagrams. Here we have just the structure with the lines. The space filling model just shows the sort of the clouds overlapping. These all are showing the same thing. Water is H2O. So hydrogen forms 1 bond. Oxygen forms 2. So this molecule, H2O, is very, very stable because the valence shells are filled. Methane, we'll get to more of this later, is CH4. Carbon has 4 valence electrons. Overall, it has 6 electrons. It has 2 in the first. Can I do this with my hands? It has 2 in the first. So 4 in the second. It wants 8, so it forms 4 bonds. Methane is CH4. Hydrogen forms 1 bond. So you need 4 hydrogens to make the carbon happy. These 4 you should really have memorized as to how to draw them and what the electrons are doing. This is just showing the same thing, just zoomed in. These are all from the textbook. So this picture, this is a common AP style question. So this would be a multiple choice. I have 4 molecular structures. I'm sorry, I have 5 of them. 1 of them is wrong. Now I forgot to say one thing. How many bonds does nitrogen form? Let's do that real quick. So nitrogen is 7. So 2 electrons in the first, 5 in the second. It wants to have 8. So nitrogen forms 3 bonds. So you should just have this memorized. Hydrogen forms, let me go back to the question. Hydrogen forms 1, oxygen forms 2, nitrogen forms 3, carbon forms 4. Write that down. That just memorize. So like look at choice A. Are there any atoms that break those rules? This hydrogen has 1 bond, this oxygen has 2, this nitrogen has 3, each hydrogen has 1. So A is a fine molecule. Take a minute and then look at the choices and see if you can find one that has a bond to an atom where you've broken the rules. I see it already, but I don't want to give it away. If you look at D, for example, D looks weird. Carbon, double bond, oxygen, 2 single bonds, hydrogen, but this carbon has 4 bonds, right? So it's happy. The answer is C. This oxygen has 3 bonds. So this is, I mean, if this exists, it's unstable. C is the one where you've broken the rules. B is methane, and that, you know methane. You know that exists because we just did it a minute ago. Okay. Electronegativity. Oh, atoms are like schoolyard bullies. They tend not to share the electrons equally. Going back to the periodic table, in chemistry, you probably learned, so electronegativity is a measure of how strong an atom pulls the electrons. Electronegative atoms are bullies. They hog the electrons. The most electronegative atom is fluorine. If you remember this from chemistry class, fluorine is the biggest bully there is. And the way the periodic table works is when you go down a row, you get more electronegative. And when you go up a column, you get more electronegative. The noble gases here are inert. They don't do anything. So what's more electronegative, fluorine or oxygen? Fluorine is. Chlorine versus bromine, chlorine is. Carbon versus nitrogen, nitrogen is. Fluorine's the biggest bully there is. Biology doesn't love a lot of fluorine, but it likes oxygen. So the biggest bully in bio really is oxygen. And oxygen bound with a hydrogen, the oxygen's gonna hog those electrons like crazy. The poor hydrogen is gonna lose the battle. Bonds that are non-polar are where the electrons are shared equally. So if I have two carbons bound together, well, they're both carbons, so the electrons are shared the same because they're the same atom. Oxygen's a bully. Two oxygens bound together, they're both equal bullies, so it's non-polar. Things that are polar are when you have a bond between two atoms where they're not shared equally. Something just to kind of file away, a CH bond, carbon and hydrogen, you might think that would be polar because carbon's further down, but they're about equal electronegativity, so a CH bond is pretty non-polar. Things like oils are non-polar. Oil is lots of CH bonds. The biggest bullies would be like an OH bond or an NH bond. Oxygen and nitrogen are pretty electronegative. They're bullies and they don't share well with hydrogen for sure. So this picture, so polar covalent, unequal. Non-polar covalent, equal. So this is a picture of the water molecule. This Greek letter is a lowercase delta, and in science that means partial. So a water molecule, H2O, the oxygen hogs the electrons more than the two hydrogens do. So this side of the molecule has a negative, it's called a dipole, a partial negative charge, and the two hydrogens have a partial positive charge. Those are not, like the OH bond, what the arrow is showing, that's a covalent bond, right? But I could have a bond between water molecules, between say the O of one and the H of another one. That's called a hydrogen bond, which are weak bonds, but they're weak bonds between dipoles or partial polar charges within, well, the bonds are between different molecules, but the dipole forms within a single molecule. We're going to come back to hydrogen bonds in a minute. Ionic bonds. So sodium, let's go back and look at the table. Sodium has 11 electrons. If it had 10, it would be stable. So sodium really wants to lose an electron. Chlorine has 17. If it had 18, it would be inert. It would be happy. So chlorine wants to gain an electron. So what tends to happen is that sodium just gives its electron to chlorine, which makes the sodium positively charged, the chlorine negatively charged. So overall, that's sodium chloride, that's table salt. That's an ionic bond. It's like the most unequal sharing because you're not sharing. You gave the electron to chlorine. In the realm of sharing, non-polar shared equally, polar shared unequally, ionic, they're not shared at all, or it's the most unequal sharing because you gave the electron to another atom. How do you break ionic bonds? Usually you just put it in water. You can dissolve table salt in water, right? So the bond between the sodium and the chloride will be broken or disrupted just by water. Now, does that mean you've gone to elemental sodium, which will explode, or chlorine gas, which will kill you? No, you still have Na plus and Cl minus. You've just broken the bond with water. Water interrupts the ionic bonds. A cation, sodium is a cation because it's positively charged. My high school chem teacher loved cats. Cats made her really, really happy. She always wore kitty cat sweatshirts. So cats were positive to her, and cations have a positive charge. Still to this day, I remember cations are positive because of my high school chem teacher. She was very interesting. Anions have a negative charge, so chlorine is an anion. And an ionic bond obviously is a bond between a cation and an anion. Salts are just what you call ionic compounds. Is every salt sodium chloride? No, you could have calcium carbonate, or really any bond between a cation and an anion is a salt. Hydrogen bonds, we discussed this. So hydrogen bonds, here's water. We've done the dipole nature of water. Ammonia, NH3, NH bonds are polar because N hogs the electrons. So in ammonia, if I go to Publix and buy ammonia, like to clean my floor, and I put water in it, they'll mix. You can dilute ammonia, right? So ammonia and water mix. Well, they mix because they're both polar. The hydrogen is a positive or partial positive charge. The nitrogen is a partial negative charge. The dots here represent a hydrogen bond. Again, this bond or that bond, these are covalent bonds. You can break those, but those are difficult to break. These bonds are covalent. They're difficult to break. Hydrogen bonds are very, very easy to break. You heat it, you'll break a piece of cake. Yeah, okay, so polar things like water or ammonia have what's called hydrogen bonding because the hydrogens have a partial positive charge, okay? Van der Waals interactions, you ever seen the picture of, it's called the Jesus lizard? I might show you this in class. It's the lizard, the little gecko thingy that can like run on the surface of the water really fast. Van der Waals interactions, so say you have a molecule that's pretty nonpolar, but like for a second, the electron's a little bit off center because electrons move around. You might get like temporary hotspots of partial negative or positive. These are called van der Waals interactions. They're very weak and they tend to move around the molecule. Excuse me, but they can have an effect like the little gecko lizard has little hairs on its toes, which increases the surface area, and it can walk on the water, whatever. This isn't that important, but just recognize that van der Waals interactions are like temporary dipoles. Hydrogen bonds, they're not permanent because they're easy to break, but they're, the hydrogen bond, the water molecule is always polar. Van der Waals could be in things that are non-polar, typically, but you have like a partial moment where the electron's off center. Collectively, they can be pretty important. And there's a little gecko, he's such a cutie. Okay, shape. Shape is everything. In biology, shape is everything. It's everything. If you change a molecule's shape, you screw it up. Water has this shape. This angle is 104.5 degrees. Methane has this shape. It's sort of like a tetrahedral. Is this tetrahedral? Like if I have a one coming up top, then a stool with 3 legs, that shape, is that a tetrahedron? Whatever. They have shape, and the shape dictates what the molecule does. This is a picture of, we're going to talk about drugs and opioids and endorphins and all that much later in the book. But, morphine is an opioid. Morphine is a drug that makes you feel really, really good. If you're in pain, a shot of morphine, the pain goes away. Endorphins are molecules that your body makes naturally for very good reasons. The runner's high is caused by endorphins. If you look at a natural endorphin, like dopamine or whatever, we'll get to all this later. Look at the structure of the molecule. This part right here binds to opioid receptors in your cells, which are natural. This right here is natural. Morphine is a molecule, again, it's an opioid made from poppy plants, that mimics, it's a different molecule, right? But it has the same shape in part of it, and it will bind to the receptor also. So it'll have the same effect because the structure is the same in this part of the molecule. If I took natural endorphins, if I changed the shape here, then it wouldn't bind and they wouldn't work. If I change the shape over here, it might not make a difference, but it actually could, but maybe it wouldn't. This is one of the themes of biology, which we're going to come back to all year. A molecule's shape determines its function. Form fits function, all right? The structure tells you the function. If I change the structure, you change the function. I think you get the idea for right now. Okay, really quick chem review. In a chemical reaction, on the left are the reactants, on the right are the products. The reactants make the products. Here I'm making water with hydrogens and oxygens. You can see where the bonds were. You can see where the bonds are now. You change the bonds. The arrow means reaction. And notice this is a single-headed arrow. This reaction's only going in the positive direction. When we do chapter 8, we'll discuss photosynthesis. It's a very important reaction. We'll come back to that. Chemical equilibrium, notice this diagram right here. A plus B gets you C plus D. This is a double-headed arrow, which means the reaction goes both forwards and backwards. Equilibrium is what you call it when the forward and reverse rates are the same. So if this reaction has reached equilibrium, and this is an important concept, it doesn't mean the reaction is stopped. It just means the forward rate and the reverse rate are the same. So in a second, if I had the forward reaction happen 10 times, the back reaction happen 10 times, it's like nothing is happening, right? The reaction is going on, but the rates are the same, so you're at equilibrium. Again, it doesn't mean the reactions stop, it just means the forward and reverse rates are the same.